Okay, hello, welcome back to another one of my video log recording sessions where I talk about genetic algorithms. Date and time is 2025 June 13th, and the time is 1:08 or 8 past 1 a.m. So, well, it's been a while since the last time I recorded. Since the last video log session. 5 days actually. So it's not that long ago, but still, because I usually did it every 2 or 3 days, but this time it took me 5 days. But for good enough a reason, I hope. I seem to have bitten off more than I could chew, or maybe not, but then again, when am I ever sure, right? So here's what happened. It's nothing grave, it's nothing serious, but here's how what I've been doing. So when I first when I first started talking about doing dynamic genetic algorithm, I said that there are several ways of doing this, and those are, as I'm going to list them out. Those are these rows. Actually, these settings, rather. That's the better way of saying it. Chromo length, or which equals num items, or chromo length is equivalent, as so far, chromo length is equivalent to number of items or number of genes. Yeah. So for the first 2 or 3 to 4 months, what I've been doing is this fixed. The first one is where utility values, constraint values, and chromo length or number of items is fixed. And then for about a week, or for about 2 weeks, I covered this, where the utility values were fixed and constraint values were fixed, but the number of items or chromo length would vary. Either go increment, either plus or minus, and usually from what is called usually from what is called one era to another. I keep spelling that era. It's era. It's like era 0, era 1, era 2, all the way to era n. And there were usually 10 eras. So it'd be up to, for example, until era 9. So this I've done. The second setting, the second row, I've done, and then there would be 6 other settings. So namely fixed, varying. I should do that. Varying, fixed. Yep. And then fixed, fixed, fixed varying. That I've done. Fixed varying fixed. I'm looking at the sheet of paper that I have, and fixed varying, and then another for. Oh my god. I'll have this in blue. I'll have this in orange, and the rest I will just keep them in red. Fix and then varying. No, actually, let's do that. Fixed, varying, fixed, varying. No, actually, just one varying each. Actually, no. Varying, fixed. No, we have that there. That's 1, 2, 3, 4, 5, 6, 7. This should be the 7th one, which is varying, fixed, and the last one, but not the least, varying. So these are the 8 settings or 8 combinations in which dynamic genetic algorithm can be performed. And well, here's the thing. This I've been doing for like 3 months. Is it 3 months? Let me just check. Yeah, approximately 3 months. 3 meses, or 3 months. And this I did for 2 weeks. But because of the for these 6 of them, because of the way they can actually implement it, took me around 2 days to execute and perform. And also because I had done so much work up until now, I could reuse the code from there, and then that's what happened. So for the past 5 days I did all these 6 of them, but yeah, actually I did that, and that's the end of this sentence. I did the 6 the rest of them. And in this video log session, I'm going to go through them and share them. But I just wanted to give myself the excuse of why it took 5 days to make this video. Also, I feel that just one video about all these 6 settings on all these 6 settings on how to do or related to dynamic genetic algorithm, one video does not do justice. So I think because number one, I have to be honest, I do not know fully yet what I'm looking at. I'm trying to interpret the results in as many ways with as many methods and techniques as possible. Not that I'm that clever or smart. I'm just trying to what I do is just try to be resourceful. But yeah, I don't think one video is going to do the justice. So maybe it will be in total all these 6 for for all these 6 settings, it will be maybe 2 to 3 videos, maybe, depends on what I find out as I go along. Yeah, so that's you know, out of the way. That out of the way, let me just move this, literally get it out of my way, out of the screen, and let me just go through what I have done in order to implement the rest of the the rest of the settings or methods. So what happens, or what needs to happen for when I need, what needs to happen for utility values or constraint values if they need to quote unquote vary or change. For now, I just made them so that, for example, I would have some utility values here, right? And then, oops, let's do it. I have 100 utility values. So I would take all these values and have them be within their own distribution, something like a normal distribution, but maybe with a different standard deviation for each value, because the same standard value for 100, and well, if the standard deviations, did I say standard values? If the standard deviations for an item with a utility value of 100 and for an item with a utility value of 5, if it's the same standard deviation, then the I don't like that color. Then the difference is going to be so big, so huge. So because if the original or the default utility value is 5 and I put it as something like 1 or 2, then if this is 5 here, if the standard deviation is too big, the value could actually go negative, which is not great. I mean, this could work because there could actually be an instance where where actually packing something can actually impact your summed utility in a negative way. But for now, that functionality is actually or not actually, it could kind of be said that that functionality or that interaction is kind of reflected in the constraints list. So yeah, I didn't want to make things too complicated. So the standard deviation should not be the same. Standard deviation for item 1 should not be, or does not necessarily have to be the same, and should not be the same as standard deviation for item 2 or 3 or 8 or 89, whatever, in terms of absolute value. So if that's not the case, I should also not have the standard deviation of an utility value that is where the default is 100, and I shouldn't and then if I had another item where the default value is 10, I shouldn't have the same standard deviations in terms of absolute value, but I should also not have the standard deviations be the same percentage of the default value. So if the standard deviation in this case is 2%, then it's 2. Yeah, right. And then in this case it's what, 0.2. Because the way it works is that if it's 2 or 3, whatever, then the distribution of this item's utility value is going to change so much, and it's going to impact the performance or the fitness of entities every time it changes a lot more drastically, a lot more. The impact is going to be a lot bigger than when, for example, if this item changes. So no. So what I did is, for bigger values, I would have the standard deviation be a smaller percentage of the original default value. For smaller utility values, I would have them. I would have the standard deviation. I would have its standard deviation become a slightly higher percentage of the default value. I don't think I have that here, but I think I'll share it next time. So that's how it goes. That's how the values are kind of decided. But I have not yet mentioned when they're decided. And these values, if we were to say that these are the standard or default values, they would change, or they would be generated or change per generation. So over maybe 1000 generations, the average of the first utility value would be around 100. But it doesn't guarantee that from generation 1 and generation 2 does not guarantee that the utility value of the first item stays at 100, or maybe even 99. I set them all so that they become integers, not floats or decimal points, whatever. They're all integers in this case. So things will change, and in the next generation to come, it could be 102, and then generation 4, 105, and then suddenly generation 5, it could be 96. So within a certain distribution, the mean or the average will still be the default value, but every generation, within each generation, or every time every time a new generation is started, the utility values will be fed into a function and will be reborn into a new list of utility values list, where the numbers were sampled from some specific from a normal distribution with some very specific parameters. I think that's the right way of saying it. And this is the same for the constraint values as well. So that's what I needed in order to carry out the 6 remaining settings for these bits, because I needed them to change per generation in every generation. So that's what I did. And I'll be even more honest by saying that let me me also get that out of the way. As I started the dynamic genetic part, I still don't know, or well, I know a bit. Well, I think I know a bit more. But as I started this new series chapter, I guess, I did not really know the purpose of this chapter. Why am I doing this? Why do this? What am I testing? Like, does it work? Does it not work? And if I feel that it works, if I think it works, and what do I mean by it works? What am I looking for? What am I assessing? On that, I still don't know exactly. But for now, I have one thing that I can look for, or I've come up with one thing that I can look for, and that is because I know with 99.999% certainty, I'm that much sure that by now that with lower constraints, actually constraints, or rather lower max constraints, that is where for 100 items I'm supposed to find, or the entities cannot be above 18,000 units in terms of max constraint or constraint values. Maybe, and I'm sure I said that it's supposed to be in grams in this case, but anyway, so 18,000. Do not go above that. 18,000 is okay, but don't go above 18,000. And since I know that with this setting, with these preset values, I know that for now 2865 is the true ceiling. I know this for, yeah, kind of quite sure, very quite sure. So what I can do is, while I'm testing, or what with the so-called experiments of these 6 settings, what I can do is see and check if these 6 settings were able to yield entities that converge to the true ceiling. But what's the true ceiling? How do I know what the true ceiling is if the constraint values and utility values change? If these fluctuate, how do I know? Well, I cheated. Well, I don't really think it's cheating, but it can feel like cheating. When the evolution is done with all the entities, I would go through all the entities that were, all the entities that were ever created within that evolution, and calculate the summed utility values and some constraint values with utility values and constraint values fixed. So here's the thing: when the evolution was being carried out, when the evolution iteration was being carried out, any one of them, or all of these 2 sets of values, could have been varying. It's like any one of them. and, or rather, but, well, let me rephrase that. Any one or all of them were varying per generation. So in every generation, the set of values that were, that were to vary were different. But when the evolution is done, when the 1000 generations have passed and the computation is finished and done, in order to find the true ceiling, what is supposed to be the true ceiling by now, 2865, I would use the fixed versions of the utility values and the constraint values. So let me explain that again, so that I can try to sound coherent. So maybe for this setting, the constraint values are varying, and when that is done, all the summed utility values and the summed constraint values of all the entities that existed in this setting would be calculated to find any combination or any chromosomes rather, that is 2865, or maybe, if I get lucky, above. So how? Although this constraint values were set to vary, when calculating this, they would all be fixed. And same for the utility values. So that's one combination done. For this combination, well, the number of items would change, but that's no big deal. That's okay, because that was covered here. So the summed utility plot would look something like this. And to assess the validity, or to assess the performance of this setting again, or to assess the effects of this setting, where the constraint values also again varied along with the number of items, the constraint values would still again be fixed in order to find any chromosomes that scored above 2865 or 2865 with this summed constraint value equal to or below 18,000. These two criteria, these two conditions. So yeah, and for this one, same thing, but I'm going to repeat myself. The utility values are set to vary, but for the after, when everything is done, the utility values will be fixed again to find entities that meet these conditions. Again, same for this. Number of items varying, but that doesn't matter because I'll be getting that one, so that's okay. Utility values varying, constraint values varying. Again, those two sets of values will be fixed for assessment after the evolution iteration. And for the last one, varying, that's still okay because I would still be getting this, and I would have these two sets of values fixed, not varying, in order to assess the impact of this setting. Because what do I want to know? I would like to know if dynamic, am I spelling this right? If doing things in the dynamic way is number one, or rather, if doing things in the dynamic way no, let me rephrase that. I would like to know how doing things in the dynamic way is different, if it's beneficial, if it actually could potentially provide any benefits. You know, what are the advantages? What are the disadvantages? I know one disadvantage: it's a lot more complicated to implement. What is the advantage? I don't know yet, but maybe I'll find out as I do this video, or maybe the next video. Yeah, and while I'm doing that, I would like to know if doing things in the dynamic way, I can find. What do I want to find? If I can find the true ceilings. If there's only one true ceiling, or if there's like more than one, I would like to know the true ceiling, or what the true ceiling or ceilings are, and if doing things this way can also lead me to this. That's what I would like to know. Well, and spoiler or short answer, yeah, it does work kind of, but that's what I'm here to share, isn't it? So the first ever thing notebook, or the first ever run that I did was oh, that's so many. I think this is the first time I record this bit of the code. I have done so many iterations. Anyway, the first ever in this case was called Vanilla 2025 0610, and this is called Vanilla because this is not dynamic at all, but this is like the benchmark. And when I do this for, what is it? Yeah, there we go. For 1000 generations, so that's one era, for 100 items, number of items, and for 1000 entities in that population. With all this learn rate and candidate method implemented, with lower individual mutation rates and, well, individual mutation rates using lower base mutation rate. So when I do this, this is what the sum utility plot looks like. So this is until the very first 100 generations. One thing I would like to brag. Not a big thing, but I mean, I would like to take the small win by now, because this is just way above my head. I have fixed the plots so that now they reflect the number of entities when this snapshot was taken. So I think that's a very good improvement. It is a small one, but hey, until generation 200, until generation 300, until generation 400, until gen 500, 600, 700, 800, 900, 1000. So these plots are very, by now, familiar. I mean, I've been seeing this pattern for the last 2 months, so let's leave that off. That needs to go. And here are the distributions. This is well, 100, 200, 300, generation 400, 500. Let me start from 100, 200, 300, 400, 500, 600, 7, 8, 9, 10. So I know I said there's only one era, but again, in the usual setting, it was when I was doing things where the number of items would change, because every 100 generations was equivalent to one era. So that's why it says era 9 here, which is the 10th era. But anyway, one thing to note is that because I'm doing everything in one whole go, as opposed to what I said when I had varying number of items, and I concluded that increasing the number of items along with increasing the number of entities within that population is actually quite beneficial, because it saves time, it saves all the computation. Yeah, so it's a lot more efficient and just as effective. But anyway, since I'm doing everything in one go, 1000 entities, well, starting with 10 entities, but quickly going up to 1000 entities, you can see that many entities have actually kind of converged very early on, as early as between generation 200 and 300. See, you can already see that the top entity has 2865, and that's actually the mode. So all that is just it's just entities with true ceiling chromosomes. Same here, same here, same here, same here, same here, same here, same here. So they quickly converge because they were the entire environment was already sufficient for a very early convergence to true ceiling. So that's how it went. But the next one is this. Should I cover this? I don't know. Maybe I will. This is what happened. Next, but there's one caveat here, is that I made a mistake and I had the population grow. Although it's one whole era, I had the population grow from 100 to 1000. And here are the results. You can probably see that within generation 200, it's already getting quite close to 2865. But because there's not like 5 times fewer entities, 20% of 1000 here, so that's why the entities have not yet fully the entities on the right here have not yet converged. So with the population growing by 100 entities every 100 generations, the entities have actually failed to converge. No entity had ever reached the true ceiling, because the max ever was 2832. But is that true? Is that really true? No, it's not, because that was a trick question. This is where the utility values would be varying, following some sort of a normal distribution. So it is quite natural that, or it is quite obvious that because the utility values would be changing in every generation, we don't know if there had ever been an entity somewhere here where they had actually had the right true ceiling chromosome, but the resulting value, that is the resulting sum utility value in that generation, was not 2865, or maybe below 2865, or it could even be above 2865. It could be 2870, but in actual fact it could actually not be one of the true ceilings. But anyway, this is where the population would grow per 100 generations. So this was a mistake, so I corrected that mistake, and this is that. and on the left is just everything in one go, vanilla, as it says right here. On the right is this vutil, well, it stands for varying utility, and then I have to be again, being very honest, I forgot to rename all the other instances, so I kept the vutil even when the utility values would be fixed. So that's my bad. So anyway, 1,000 generations, or approximately 1,000 generations. You can see that 49 entities have been struck out. Yeah. Quite similar, yeah. And then by generation 800, 900, 1000. So again, the maximum ever is 31 units away from the true ceiling, that is 2865, but we don't know if anything existed because the utility values were fluctuating. They would change every time. So what? Well, I had to do something to see to that. I made I made a new notebook, and then with a new part that would extract all the true ceilings, or yeah, all the true ceilings following where is it? Where did I put it? Oh yeah, following this condition right here. Following these two conditions. So equal to above 2865 and some utility value equal or less than 18,000. And when I do that, well, let's find out, right? When I do that, this is what happens. Let me just go way down. I now have to make a new notebook, or kind of JSON. I'll import JSON and work on it. Seriously? For vlog. I hope I'm recording this right. Yep. Yeah. No, go away. I made a JSON. I made a JSON file, and this thing has all the true ceilings from all the iterations that I ran. I can't say it is actually all of them. That could actually exist, because as there are what did I do wrong? This many possibilities when you have 100 genes. So it's I don't intend to try to find out all of them. But so anyway, what I want to do is find out if I had any true ceilings from the first one, which is where did I put it? Here we go. For this one, for the vanilla, there were 39. I got 39 from them. And for the first two after that, where the utility values would be set to vary, I had one true ceiling. And next one, where I had all the population size I've set to 1000 had 4 true ceilings. Now I can't say if all of these were actually unique. They were they are the for example, this 4 is the number of unique true ceilings that were found within this iteration, that is vutil 2025 0610 1 10_1. So 4 unique in this iteration, but I can't say that these 4 unique true ceilings are totally the same or different, or all of them are different, or some of them are different from any one of these new iterations that I'm about to share. So with that out of the way, again, let's go back to the plots. The next thing that I did, oh man, I did another one. I felt that I needed to do another one because I messed up. I made that mistake. This is the second time that I did it right, with all the entities there, 1000 entities approximately. And see, it's 2836. Seems to stay that way because of the fluctuations in the utility values of the items. And if I were to check if I actually got any true ceiling chromosomes, I got 20 of them. So that's actually quite decent, no? Again, $39, cool. So, well, seeing or considering that I got 39 unique true ceilings from the vanilla run, and I got 20, or maybe sometimes 4, or in this iteration 20, from this setting where the utility value, where only the utility values would be set to vary, is actually I think it's quite decent. You know, the fluctuations in the utility values don't seem to have impacted the entire process that negatively. But then again, I have to ask, then why am I doing this? What benefit does this actually serve? I don't know. Again, moving on. The second iteration, now we are doing this setting where the utility values are fixed and the constraint values are set to vary following some normal distributions, and the number of items is still fixed to 100 items. And when I do that, here are the distributions. I need to get a new mouse. Holy shit. Oh, I shouldn't have said that. The distributions, yeah. You see that entities have actually converged. This is the final state of the world, and the mode is 2865. And see here, it's easier to get 2865 because the utility values are fixed. But we just saw that there were 49 of them towards the end. Doesn't mean that there were 49 unique true ceilings. But here's what they look like. Generation 100, 200, 300, 400, 500, 600, 700, 800, 900, 1000. Now, the maximum ever is 2870. It's higher than 2865, but this isn't necessarily something to be excited about, because now that the constraint values are changing and shifting, this means that sometimes the entity could actually take more of the genes or the items. They can tolerate more constraints. or summed constraint. No, they can actually tolerate more genes or items given the same max constraint, because the constraint values are fluctuating. That's the right way to say it. I should have said that from the get-go. And so I would like to know how many unique true ceilings I got. I got 46 of them. That's quite a lot. That is quite a lot. I know that I got 46, but even when I'm seeing this again, I'm quite surprised that I got even more than when I did it the vanilla way. But again, the next one, again, the same setting. Sometimes I would do the same setting twice or 3 times. Sometimes I would do it once, but I know it's not consistent, but that's how I rolled. The next one is still the same thing, but a different run. And here are the distributions, entity distributions. They're all very, very similar. Oh, this looks very normal, doesn't it? The KDE. but so many, or a lot of entities have converged to the true ceiling, to the known true ceiling so far. 71 entities. And now it's 62. But anyway. Here are the summed utility plots. Generation 200, 300, 400. Again, the maximum ever is 2870. So it's no coincidence. It seems to be quite common. This seems to happen quite often. So with again, I got 32. So I'll just write that. What did I do? I know I could just run, write myself some new code to go through all the keys and values, but what's the fun in that? And then next thing is, the next setup is where the utility values would be varying and the constraint values would be varying as well, both following some sort of their own normal distributions, and the number of items would be fixed at 100 items, and that is still named wrong because it still says vutil. I know it's confusing. I got confused. That's why they were named wrong. I didn't actually think about changing them. Here are the distributions. So this is where both sets of values are varying. The utility values and the constraint values, and well, that's quite fun. Okay, here are 2 generation 400, 500, 600. Generation 100, 200, 300, 400, 500, 600, 7, 8, 9, and 10. Yeah. And the mode is 2826, and we cannot actually see what the maximum ever was, so let's just skip right to the summed utility plots. 100, 200, 300, 500, 600, maximum ever is 2843. Okay, so the maximum ever under this setting was 2843, but we still don't know if true ceilings existed, and if they did, how many existed. So let's go see that. This is 34. I got 34 for this. 34 true ceilings, even when the utility values or constraint values were varying. Yeah, I guess by allowing the concept of varying values for the utility values and the constraint values and the number of items, I could say that this way of evolving or evolution and doing the genetic algo things still works even when the values are not static, are not fixed. As long as they follow some sort of distribution, it would still work. As long as it's something like a normal distribution or left skewed distribution, something like that. Because from my previous videos I found out that left skewed values also quite closely mimic the behaviors of normal distribution, normally distributed values. So yeah, I mean, so anyway, even when all the values vary, I could say that dynamic genetic algorithm. Oh no, that's the very definition of dynamic genetic algorithm. Even when all the values would vary or change according to some given distribution or distributions, genetic algorithm is quite likely to work. I guess that's one of the few lessons that I can take away from this. So anyway, this was 5, where both the utility values and the constraint values would be changing every generation. The next thing is where the utility values would change, varying, and the constraint values are fixed, but the number of items would be changing along with the population. Oops. So here are the entity distributions. You can see that as the population size increases, we start getting more and more fledged entity distributions. Because right now this is less than the left half of a normal distribution at the end of the second era, third era, fourth era, fifth, sixth, 7th, 8th, 9th, and 10th. See, now we have some bit of the right half of the distribution, and we started getting that after the 5th era, and the average was 2667, and the top was 2813, and the mode was 2703. But we still don't know if we ever got any true ceilings. So let's go to, before finding that out, let's go to the sum utility plot to see if we still got the steps or the staircase. We do, and the surfaces of these steps would kind of be less than smooth, but that's because of the fluctuating values. Right? Why am I asking myself? Yeah, that's because the utility values are set to vary. But yeah, we still have the steps, which is normal, and the maximum ever was 2820. But did I get any true ceilings from this? Let's find out. No, I did not. That was sad, right? I did the same, and that's this one, 7. And I got 1 true ceiling. So, this kind of disproves or goes against what I just said 5 minutes ago, right? Meaning that bit about, oh, maybe doing dynamic or maybe doing genetic algorithm where or when the utility values or constraint values or both of them vary, still kind of works. Well, in this case it kind of didn't work, because when we usually got 39, 46, 30, so somewhere around 30 or 35 true ceilings out of this many possible combinations, yeah, we could say it worked. But in this case it didn't work, where when the utility values varied and the constraints values were fixed, but the number of items changed per era. So this didn't work. Next up is when I had the utility values fixed and the constraints values set to vary, and the number of items would start from 10 all the way to 100, along with the population size starting from 100 to 1000. And when I did that, this is what happened, the entity distribution. So we're still very familiar with this. Yep, quite familiar. And the sum utility plot, second era, third era, fourth, fifth, sixth, seventh, eighth, ninth, and no, eighth, ninth, no, this is 10th, so 9th and 10th. And the maximum ever was 2821. So we didn't get that, because this is where the constraint values were fixed. So let's find out if we did or did not. 0. We got 0. And I only did this once, because it kind of signaled that it does not work when I do this. Actually, yeah. And on to the last one, where the utility values would be set to vary, constraint values would be set to vary, and number of items could, yeah, start from 10 all the way to 100, along with the population size 100 to 1000. And so therefore that's 10 eras, 100 generations each. Some utility plots. Yep. Again, here the maximum ever is 2832. Wow, that's great. Oh, let's look at the distribution. So again, quite similar to what we've been saying. And how many unique true ceilings have I been gifted with? Let's find out. 7. Yeah, somehow this kind of works. So it's quite odd, because naturally, or I don't know if that's the right word, but naturally you would think that if more things were set to fluctuate and change, that would give you, that would actually yield somewhat unstable results, or worse results when it comes to converging, in terms of converging to the true ceiling. But somehow, if all things were set to vary, I got 7 unique true ceilings. But when 2 things were set to vary, this is 1. When 2 things were set to vary, I got 0 and 1. 2 things being, what was it? Utility values and number of items. And then when the constraint values and the number of items along with the population size, were set to vary, I got 0, or it's very likely 1 or 2 only. But compared to that, 7 is quite a big leap. And so you might, it would be quite natural to think or to wonder how many unique true ceilings that every iteration, every one of these iterations that I did for the past few weeks have actually given me, right? So let's find out, and you'll see what a terrible programmer I am. So for, let's just say item, for key in, oops, print what else? Then okay, double quotes, length, there we go, there we go, there we go, there we go, and hope it works. Why not? Print key, yeah. What am I doing? Oh yeah, I'm so dumb. There we go. So, here. Oh, that's a bit of a spoiler. So far I have found 220 unique true ceilings. Unique as in across all these iterations. And what I used from the last video, when I used any one of the 7, or is it 8 procreate functions, none of them actually gave me a true ceiling. So which kind of justified, which was the excuse that I used to justify me using the new measures, namely individual mutation rates and the learn methods and whatever, and the lower base mutation. Actually, I think it was those two: lower base mutation and individual mutation rate. And then when I did things in the responsive way, I had 37, 6, and 2. In this one I had 11, so I got quite a few, and I just collected all of them together, and I again sifted them and then filtered them and got the unique ones, and now I have 220 unique true ceilings. And that is this much out of and 222 is this much percent of this ugly, huge, terrible number. I know, I just wanted to show that, you know. So, what did I find out? Well, I found out that sometimes it does work, sometimes it doesn't work. But I think the fact that it sometimes does work was worth finding out, was a fact that was worth finding out, right? Yeah. But one thing that I can actually do, probably, is maybe I should or shouldn't do it, but another new idea could be that for now, this, for example, this set of values, the utility values list changes per generation. And that's the whole premise of it. What if I change this to like, for example, the values would still be fixed, certain values, or they could still fluctuate, but I could have each entity react differently as to how they digest the utility values and how they handle the constraint values. So, for example, one entity A, named Rachel. What's a good name? Rachel, I don't know. Rachel Windrunner, or whatever. Right? Rachel Windrunner. This entity has the tendency to take the first item with a utility value of 100, for now fixed, but this entity has the tendency to take this fixed value and digest it, or take it as 105, and maybe takes this value of 30 and then takes it as 22. So it's an individually dynamic when it comes to utility values and constraint values. Of course, the given preset sets of values could also still be fluctuating or varying, but the way an entity, or the way that entities the way that the entities digest or handle values could be different, as in the amount in the percentage of how they take it, or how they don't take it, or how they handle it. So, for example, again, where's my mouse? Oh, there we go. I'm just going on and on. Entity B, named Phoenix. What's a good name? Phoenix Ramirez. Is that a good name? I don't know. Phoenix Ramirez takes a constraint value that is fixed for now of 1,500 units, and then has a tendency to, take that in an easy way, to ease this constraint and take it as 1,400. But unfortunately, for some other item where its constraint value is 200, our dear Phoenix would take that as 290. So something like that. So tendency to take utility values and constraint values dynamically. Yeah, and while doing that, of course, these tendencies would still have to be, preset, or they could also these tendencies could also lead to a normal distribution of some sort, but I don't know. But the overall purpose of this would be to see if true ceilings are attained through this method. Yeah, I think that's a good objective. Okay, that's about it. Thanks for watching. Okay, really, thank you for watching. See you next time. Bye.